All right, good afternoon, everyone. Let's get started with today's class. So I just sent maybe 10 minutes ago an email to you all asking you to create a new project. And I uploaded 4 files to GitHub. So 3 of them are going to be data related. We have 2 TIFF files and 1 GeoJSON files. And then the other one is the partial script. So I ask that you do the whole thing as you already know, as far as creating the project, the subfolders, moving things to the right subfolders, and so on. And then we're going to get started on that. If you're still working on that on your side, that's all right. I'm going to just pull up here the project on my side. So I can get started here. All right. So today our goal is going to be to import some processed UAV imagery in the form of NDRE. That's the normalized difference red edge index that we talked about in the previous class during the lecture. We're then going to we're going to talk more about what the imagery represents. But then after importing that image, we're going to create a variable rate nitrogen grid that we will supply that to a variable rate equipment to apply. We talked about this algorithm last class, the Holland-Shepard's algorithm. We're going to basically apply that algorithm to this data set and use that algorithm to basically calculate the variable rate nitrogen prescription. And then with that, so by merging the sensor data from the UAV mounted sensor with the algorithm, Holland-Shepard's, we're going to create this prescription, this imagery-based variable rate nitrogen prescription. Then we're going to export that prescription and also validate that variable rate nitrogen application as well. So if you're all able to create all the folders and project and have everything set up, we're going to get started here. So first off, as always, let's load the packages. So make sure you run that chunk. All right, so our next thing is going to be to bring in this data. So something that's going to be slightly different now, I think is the first time we do this in this class, is that we're going to be bringing a TIFF file, which is a file extension that we use for raster geospatial objects. And so in this case, because we're bringing a raster file, we're going to use read stars, right? So remember, stars is the package we've been using to manipulate raster data. Let's go ahead and type read stars. If you move the files to the right place, they should be in your data folder. So // navigate to data, and then let's bring in the NDRE pre v12.tiff. Don't run this yet. Hold on. So as you're going to notice, when you do bring it in, if you were just to run at this point, this is a large file and it has, very small pixel size. And therefore, it can be a little bit tricky to manipulate in R. And so what I want to propose that we do is that we decrease the spatial resolution right here upon reading, just to help us to be able to create analysis that are going to run faster on your computer. So if you do a pipe here, we're going to use st_downsample. That is the function that we're going to use to downsample this, or in other words, make it a little bit coarser. Here it has an argument for n, which is the number of pixels that we want to downsize. I wanted this to be equals to 3. And before you run it, because again, this may take a little time if you run it at this point. So before you go ahead and run it, I just want to rename the column. So the column is going to come with the name ndre underscore pre underscore v12.tiff. So basically the name of the file is going to be the name of that column in our stars object. I just want to rename that already to ndre only. So if you say this, you're basically renaming on the go. So now go ahead and run that. It actually imported pretty fast. If you print it, we can take a look at what is showing up here. So basically we have our spatial resolution, which at this point is 46 centimeters or 0.46 meters. We have one layer of data here that we just renamed ndre that is ranging from 0.06 all the way to 0.37, and it has about 10,000, or it has about 100,000 NA values. This is just because it's an image from a whole field, and it's a drone imagery, so the spatial resolution is really high. Also, we can notice that it is in WGS 84 UTM zone 14 north. So this data is coming to us directly from Nebraska, and that's why in this specific case, we're using a different UTM zone, zone 14 in this case. All right, we're gonna make some plots here to visualize this, or some maps to visualize this layer. But before we do that, let's also bring the plot layout of this study on this next chunk. So on the plots, we're gonna call read underscore SF. Now it's gonna be a vector geospatial file. Quotation marks, dot dot forward slash to get outside of code, go inside of data. And now you wanna bring the plots.geojson. If you bring that and you print it, you're gonna see it has 13 rows because it has 13 plots on this field. And then we just see the different columns here. Before we talk about the columns, I just want you to notice that, we have, well, I guess the main thing that I dislike about these column names is that they have uppercase. So just to make it all lowercase, just to help us type in more easily, let's right there on that plots. Let's just connect a pipe and do a janitor : clean names, just to make things more standardized. All right, so let's take a look at the treatment column. So this column here has the values reference, grower, and sense. And that's all the values it has. And I want to tell you what that is. So basically, this is a study. It's a non-farm study, the one similar to the one that I showed you in lecture with that video, where it's an on-farm study where the grower has applied whatever it is their treatment, or their not the treatment, but whatever is their traditional practice. That is what the grower treatment represents, is whatever the grower was doing. Which in this case here was applying 145 pounds of nitrogen per acre at planting. And then we have the reference treatment, which we applied a higher amount of nitrogen at planting, 250 pounds per acre in this case, to make sure that this reference on the field is not nitrogen limited. And so we need that reference in the field. If you remember from the lecture, we need to have the reference that we know that in that reference, at least nitrogen is not limiting. Perhaps other things could be limiting, but nitrogen should not be one of them. And then we have the sense treatment, which is those strips that were receiving variable rate nitrogen during side dress or in season, right? So these rates that we're seeing here, the rate pound per acre, are all the rates that were applied as fixed rates. So even on the sense, which is the variable rate nitrogen study strip, even there, of course, it received a fixed rate of 0, so it did not receive any nitrogen. But all the others were applied in a fixed way, and they were all applied pre-plant, these rates. So with the sensor base, most of the time you would apply the sensor base variable rate prescription in season because you have to have a crop growing to give you the response you need, right? It's at least using crop canopy sensor based variable rate nitrogen management, you cannot do that pre-plant because you don't have plants, right? You need the plants to be there to tell you how much stress they're under. So that's the reason why these rates are all applied at planting or pre-planting on a fixed way. And then we come in as side dress, in this case, every 12 in corn, which means when corn has about 12 fully developed leaves, and then use the sensor to determine the rates. All right, so now, as always, we're going to do some EDA. Now, the first thing I want to do for EDA here is to do a density plot to look into the statistical distribution of the NDRE data, not the geospatial distribution, but the statistical distribution. One thing about it, I don't know if we've done this before, but right now our data is in this object called pre-NDRE, which is a stars object. Differently from SF objects, star objects don't really give you easy access to the data itself unless you're using geom stars. However, to make a statistical distribution plot, we're not going to be using geom stars. We need to use geom density. Because of that, we need to give a data frame and not a stars object to ggplot. So one way we can do it, if you just pipe this pre-NDRE object into the function s.data.frame, it does work. So it gives us here about 658,000 rows. Those are how many pixels we have. We have X and Y, which are the UTM units of the position of each one of those pixels. And right now we're seeing a lot of NAs, and that's just part of the imagery itself. But we do have data, I promise you. So if to check that, we can just plug this as data frame, use a pipe, and just plug that into a function called summary. As you know, summary is going to give you a summary of the data. So we see that NDRE here is ranging from 0.07 to 0.38, and it has about over 100,000 NAs. So it just happened that those first rows that we could see were all NAs, but we do have data here. We have about 500,000 rows of data in this data frame. All right, so I want you to delete the summary function. I just use that to show you that we do have data, but we're going to plug this into a ggplot. Now that it is, so let me just rerun the until as data frame so you can see again. This is a data frame. And we can pipe that right into a ggplot. So now we're going to say that in our AES, aesthetics, I want to say X equals to NDRE. And then we're going to call it geom density to look into the statistical distribution of NDRE. So if you do that, this is what you're going to see. And so again, we do see that the mean response is probably here around 0.27 maybe. But then we have some values that are really low and some that are a little bit higher than that. But for the most part, maybe except for this long tail here, but for the most part, it looks pretty normally distributed, our NDRE data. All right. So our next step now is going to be to create some maps. So let's go ahead, do our first map here. It's going to be a static.
Sorry, Dr. Bastos, can you show again the script before? Thank you.
Yep. Were you able to check what you need?
Yes, thank you.
Okay, awesome. All right, so our next step here is going to be to create a static map of NDRE. And I'm already assigning that to an object because I will like to bring this map back again towards the end of this script. So that's why I have the 3 dots there. So I left you here some of the code. And again, I want to plot the pre-NDRE object. Can somebody help me out here with what do we need to fill on these first 3 dotted points here? So Aman is saying genome, or she said stars. I'm guessing she meant genome stars. All right. Yes, that's part of it, but it's not the whole, at least on this line of code, is not the whole thing yet. So we need something else here. Anyone in Tifton wants to jump in? So if we just say jump stars here, it's not going to work because we're missing something.
Yes.
So we could change the yes, but what we're missing that is really something we are missing is the data, right? Yes, so data equals to pre-NDRE, right? That's our object. Absolutely. So pre-NDRE, we can give it a plus. As you can see on the code, I'm already changing the fill scale to Veritas continuous. And then something else here that it may not be obvious to you right now before we actually run this code, but I don't want to be running earlier because it may take a little second here to run. But if you remember, geom stars does not change or geom stars changes the y and x axis scales and range of values, so they can show as much as possible with little space, which is great for most of the time, except for when you're making maps, because you don't want to shrink your x or y axis. You want to keep them the correct range of values, so it looks like what it would be in an actual field. So on these next 3 dots here, delete them and type chord equal. That's the function that's going to force our plot or our map to be the way it should as far as x and y axis. Now you can go ahead and run it. And then you can print this object, which then may take a little moment here just because it is an imagery with very high spatial resolution. But this is what you're seeing. So this image here was collected again at the V12 crop growth stage in corn. This was a study in Nebraska. And perhaps you can tell this is part of a irrigated field. You can kind of tell the irrigated the pivot tracks on this image here. And of course, this is not the whole field, is just a portion of it, but it can kind of tell that from this. All right, so again, I gave you the NDRE already, but as you know, you don't get the band already from these sensors, right? They give you the bands, and the drone, and more importantly, the sensor that was used with that drone to fly this field was a multispectral sensor, which had different bands, and 2 of those were the red edge and the near infrared, which I, on my side, combined them into NDRE and sent you NDRE, but the sensor again is collecting the band information, right? So that's what we would see there. All right, so let me go to Tifton and ask if somebody can help me to interpret what you're seeing here. Mohit, can you help us here at least to get started with the interpretation?
The regions with uh, higher yellow color shows more reflectance of green, more reflectance of green in green area, and the higher NDRE values, and the region with dark blue patches show lower NDRE values.
Perfect. I like that, right? We normally that's a really good starting to the interpretation. We want to first understand our color scale, right? What color means low, what color means high. Perfect. Thanks, Mohit. All right. Now there are other things going on in this picture here that may jump out to you. Anyone else in Tifton want to say something about other things related to this image?
I would say generally there is an issue with the plant since they have less NDRE, ranging from 0.1 to 0.3. Maybe the plant is not mature yet, or maybe it has they are unhealthy. And on the west, plant seems to be doing better than the east. I'm not sure if I'm doing the correct thing. But on the west seem to be doing better than the east.
Okay.
Yeah.
All right. Thanks, Polly. Yeah, so I guess, I mean, overall, we do see like a lot of spatial variability in NDRE, right? I would say on the east here, we have a pocket of higher NDRE, but then we also have a pocket of high NDRE around here, although we have very low NDRE on the very western part of the field. Any other patterns that call your attention? The strips, right? Yes, so Amandeep said the strips. Maybe, I don't know if you noticed already, but there is this stripping effect, east-west direction, that is very clear on this field. So here, these strips, I don't know how many rows they are, each one of these strips you're seeing, but they're probably a good number. I would say maybe, 12, 18 rows, each one of those strips. So they're a really good number of strips. And this field here is very large. We're going to have a better idea when we use map view to view it, but it's a pretty large field. So these strips are these strips related to the treatments, right? So the treatments are applied on plots that go to east-west, east-west direction across the entire field that you're seeing. So the strips are because of the treatments. Now, I don't know if you notice, but so there is this east-west gradient coming from the treatments. There's also a north-south gradient in some parts. Like here, seems like there's an area of lower NDRE, also here, and especially towards the west part. So there's some other feature of this field that is also impacting crop vigor as we're measuring from NDRE beyond just the treatments. So let's go ahead and create an interactive map of this layer. So let's call map view pre_NDRE. If you just run that, it may take a moment just to load it for us, but it's gonna come through. Once it does come through, let's just choose our Esri world imagery base map. Huh, interesting. I don't see my data anymore. So, I mean, it should be already showing up. So let me, instead of doing here, I just want to force here. So, what was the arguments? I forgot. Let me check the documentation. So help map view, we have our map type. Yeah, so map types, I want this to be Esri world imagery. Let's see, maybe that's gonna fix me. Oh, no, yeah, Esri, world imagery, okay. Now it should work. All right, so now we can see the base map, we can also see our layer. So, yes, somebody had a question?
No.
Okay. I don't know why exactly it's not, maybe there's something going on with my map view. I wish it would turn off so I could see behind it. But anyways, here we can zoom in. So first off, you can see that this is just one part of this pivot. It's not the whole field. That's why it looks like that. But we still have a irrigation pivot through this field. And some of these patterns that you're seeing north-south are related to soil differences. So these are probably on where you see a darker color. It's probably soils that are a little bit more sandy than the rest of the field. And so we see these patterns, which you may actually also be able to see outside of just the imagery here. So some parts like these that just kind of continue that feature of the field. So it's interesting, right? Because so this imagery was before variable rate nitrogen was applied, but it was already seeing the effects of the pre-plant rate, which if you go back to our data frame on the plots, we have some pre-plant rates that were 0. That's where we really see the strips, is where no nitrogen was applied. We have some pre-plant rates of 145 pounds of N per acre and one that was 250 pounds. So that's basically, that is causing the east-west gradient and effects, but the north-south effects is basically from soil type, which I think is pretty interesting. All right, so the next thing here is I just want to make a plot or a map of the plot's layout, so you can see that here. Let's call ggplot. We're going to use geom_sf as we're plotting a vector object. So data equals to plots. And then on our AES, I want to fill those with the TRT column so we can see the disposition of these treatments. So this is what you would see if you make that plot. So we have one reference strip. That whole reference received 240 pounds of nitrogen per acre at planting or pre-plant. Then we have the grower strip, which received 145 pounds at planting. And we have the sense strips, which received no nitrogen at planting and are only going to receive nitrogen as side dress. And in this, well, everything is going to receive nitrogen as side dress. The difference is that the sense strips are going to receive variable rate nitrogen as side dress, whereas the grower strips are still going to get a fixed rate of nitrogen as side dress. So here's just some more information about that. So the grower was the nitrogen management that was specifically to that grower, that farm, which was to apply 145 pounds of nitrogen per acre at planting. The reference, again, we need that reference to do sensor-based nutrient management, especially for nitrogen. So we received a high rate of 250 pounds per acre at planting. So nitrogen was not limiting in that reference. And then the sense strips, which will receive on-the-go variable rate nitrogen application, that in this case, it did receive, so that the sense strips did receive a variable rate nitrogen application, but it was with that same equipment that I showed you in the lecture. So it was a high clearance sprayer that was applying nitrogen as side dress with a wide drop. So basically, this study here did receive variable rate nitrogen on the blue strips at V12 It's just that at the same day that it was receiving variable rate nitrogen, using that equipment, which has the proximal sensors on the boom, and the proximal sensors were the ones determining the rate. So it was sensing and applying on the go. But on the same day that that application happened, a drone was also flown over this field to see if we would have created these rates from a drone instead of the proximal sensor, would have the rates been similar? That's what this study here was testing. Mhm. So Amandeep is asking, why is the sensor base, so the sense strips have the zero nitrogen rate on the table? So that table on the plots, this rate here is the pre-plan rate. We're coming at side dress, we're coming at V12. So that is the rate that, so that rate, how much was applied at side dress is not here. This is just the pre-plan rate. Yeah. All right, so then the question that I guess I gave you some hints about it is, what if the grower has a variable rate sprayer capacity, but does not have the proximal sensor? So they could apply a variable rate prescription, but they don't have the sensors mounted on their equipment to do the proximal sensing. Could we just fly a drone and use that data instead? Well, we could, right? That's what we did, and that's what I'm gonna show you how to process. However, since flying the drone is not on the go application, like sense and apply. So with the proximal sensor, you're sensing and applying at the same time, at the same pass. With the drone is different because you have to first fly the drone and then bring it to a computer, process the imagery, create the prescription, export the prescription, and then import that prescription into the variable rate equipment monitor so we can actually apply it. So, because one part of doing that is, if you think about it, the pixel size that we are seeing here is 0.45 meters at this point. So half a meter is the pixel size. It is very unlikely that our available equipment that we have today for variable rate application, even of liquid fertilizer, would be able to change a rate at every 45 centimeters. That is just impractical, right? Imagine how fast equipment is driving this field and how fast it would have to change a rate at every 45 centimeters. It would be a lot. It would be crazy. So on the active sensor, it's basically sensing, determining the rate, and it's changing that at whatever frequency the actual equipment is capable of handling. In our case here, we don't have the equipment limitation, at least not embedded into the algorithm. So we're going to have to come up with a grid that has a cell size that makes sense for us to change rates from cell to cell, but not inside the cell. So we're going to have to make a grid. That's going to be our first step here to come up with our variable rate nitrogen prescription. Where this grid here, the width of the cell, the grid is going to be determined by the length or the swath that the specific grower's variable rate equipment can apply to. And then the length is going to be basically decided by us, the users. But you know, maybe we've been using grids of size 10 by 10, for example. So we may use something like that, or you know, it could decide to do something bigger, something smaller. It would be up to us to decide, but we do have to determine a grid cell size for that. All right, so what we're going to do here is create a grid in R. It is going to be a little bit of a different way than what we've done up until now, and you're going to see why in a second here. So come to the next chunk. Let's begin with our plots, which is the object that has the boundary, the shapefile of all the plots in the study. We're going to make a grid with the function that we've been using, That's called st_make_grid. So we've used this before. We're gonna choose a cell size that up until now, we've been just saying cell size equals 10, which gives us a squared grid or a square grid cell. So a 10 by 10. In this case, I want to give two values. So not a square grid, nor not a square cell size, but I want to have a different dimension. So I want to give the number 6 and the number 1200. So basically here, I think 6 is going to be our width and 1200 is going to be our length of the cell. If you run this, let me just do a quick map view here and see if we can explore how this looks like before we keep going, just so you see some of the limitations perhaps of what we're doing. Okay, so yeah, so we actually did a grid that has 6 meters of width, but then a very wide number. That's this number 1200. This isn't meters, right? So 1200 meters is the width of this plot and the length is 6 meters. Now, why am I doing this? Let me show you a little bit of a different way, perhaps. If I first do a map view of plots and I plug that with a map view of grid, this is what you're gonna see. Of course, our grid is like going way outside of our plots. That was just a very excessive number just to make sure that we covered our field. But if you zoom in here, we do see that now if we were to intersect this grid that we just created with the plots, we would create cells within each one of the plots. So it would have worked. It will work, as you're gonna see. One of the challenges, though, is that our grid is perfectly 90 degrees, right? It's perfectly squared out with north. But the field is a little bit tilted, meaning that if we do intersect this huge grid with our plots, we're going to have some, the angle of the field is a little bit off than perfectly north centering. And so there's going to be a little bit of a shift on the grid cells as we move from east to west. And you can maybe see that a little bit better on the boundary of the field, that you can really see this angulation. So we're going to fix that first. To just fix that angulation, before we intersect the grid and the boundary, we just want to make the grid a little bit tilted so it matches the angulation of the field. So to do that, we're going to use a function that requires our grid to be in SP, to be an object of type SP instead of SF. So first off, the first thing here is going to be for us to transform a current SF object to SP. And we do that by using the function S and then spatial, like this. So if you run that and you print grid VRN, you're going to see that now it is an SP object. It's not an SF object anymore. But now as an SP object, add a pipe, come after the comment, we're going to call a function elide. I think that's how it's pronounced. I'm not sure. But here on this function elide, it has this argument for rotate, which is the angle that you want to rotate the grid using that angle. So this was a lot of playing around on my side. I was just changing values, looking for what was the right number, and I found it to be minus 2.2. And then to make sure that the grid, so we have the grid, we want to tilt it a little bit in minus 2.2 degrees. To make sure that it tilts based on the center of the grid and not on the corners, because if it has the anchor point at the corner, it's going to do this instead of everything going up like that. So we need to define here the center, that what we want to use as the center for pivoting that in 2.2 degrees. So basically, here, my goal here is to give the centroid of the field, the centroid of the plots. So we could use here, we could bring plots, give it a pipe. I just want to break line to make it more easy to see. We could ask for ST centroid at this point. But the problem is if we ask for ST centroid right here, if you just print plots ST centroid, it's going to give us a centroid for each one of our plots. And I don't want that. I want one centroid only for the whole field. So before asking for centroid, we have to call a function called st_union, which basically unifies all the plots into one. And then we pipe that into st_centroid. If you just run this, you're gonna notice that we get 1 point only. This has one feature, is that point. But this argument center, it requires so right now this is still an SF object. It requires a pair of coordinates, more like a vector type of object. So we're gonna pipe this into a function called st_coordinates. So if I run all this, plots, union, centroid, coordinates, we get a pair of X and Y coordinates for the centroid of the whole field and not just for each plot. If you go ahead and you run this, let's see if we can make a map view again of both of these objects. Okay, it did not work. So now, for some reason, it did not work with the grid VRN, probably because, let's see. Well, it doesn't have a CRS. That's the reason why. Well, I don't want to go there right now. Or actually, yeah, we need to go there right now. I was checking my cheat sheet. So as you saw, it just lost the CRS. So we're gonna do a few things. The first one, so get outside of the elide function, give it a pipe. We're gonna then bring this back to be an SF object. So STSSF. If you run that and you print grid VRN, now it is back to be a SF object. But it does not have a CRS. So we have to define its CRS again. So give it a pipe. We're gonna use st_set_CRS. And the value we need here, which is a new value, this is in 14 north, is 32614. So if you run that, and now you print grid VRN, it should show as WGS84, UTM zone 14 north. And if we run map view, now we're gonna be able to see. If we just zoom in here, now you can tell that the grid, so look at perhaps at the lower boundary of the field, you can see that the grid is really angled to the same extent as the field is. So now we can basically go ahead and clip our grid with our field and not have that problem of angled field. So go back to the code, give it a pipe. We're gonna use the function st_intersection. So remember that we use st_intersection when you're basically merging two SF objects. We use st_crop when you have a vector and you have a raster. So an SF and a stars. Even though I said cropping two plots, but really the function is called intersection, and we just give the plots object right there. So if you do this, you print it, and now especially if you plot it, this is what you're gonna see. So you should see now just our field with different cells across all the treatments. And the last thing I want to do here is if we were creating this prescription for that study specifically, that study is only applying a variable rate to the sense treatments. It's not applying variable rate everywhere. Because of that, we would come here and then just filter only the sense strips. So we're gonna do a filter, TRT equal sign to sense all uppercase. So now if you run that and you check your grid VRN, you should have 759 features, where each one of those features is a cell that we kept. And now if you plot it, you should see those cells. Well, so we're plotting plots and grid VRN. If I just run the plot of, if I just do map view grid VRN, you should only see the cells of the sense strips, which is right here. So we will create a prescription, a variable rate matching prescription for those sense strips only, where each one of these cells is going to be able to have a different variable rate prescription. And now, if you think of it, the length of each one of these cells is 6, because that's based on the 6 here. The 1200 was really just an exaggeration, just to get a grid that went beyond the field. But because we clipped the grid with the actual plot size, then we just remain the width of each cell being the width of the plot size, which is the width that this that the implement here that is going to be used is going to apply to this field.
So Bastos,
Yes.
I can't execute this code because I don't have the function elide.
Okay.
When I try to load the package, tells me that when I try to install the package map tools, it tells me that it doesn't exist.
That is weird.
I
So
was also having the same issue.
Yes.
They gave me a different package and I looked online, and the package I'm using is called, it's AW Try it and probably it's going to work.
did that work for you, Polly?
Yes, it's working.
Interesting. Yeah, so Marco, you're saying that if you try to install map tools, it doesn't work?
Yes.
It doesn't work. Okay.
Package
And it gives me the message error, object map tools not found.
So if you do install dot packages map tools, it doesn't find map tools. Do you want to restart?
Yes, map tools is not available for this version.
Let me see here. I'm trying to install. So I recently, well, I installed the first time. It's been a while. Okay, so warning, my tool is not available for this version of R. Okay, so maybe the version of R is not available. So maybe when I installed it, it was a previous version of R. Okay, so let's do this. I think Polly found a solution. If maybe Polly, if you could post that on GitHub, so people can know what is the solution here. What I'm gonna do, because I do want you all to still be able to follow along. What I'm gonna do is I'm going to export. So you don't have to do this on your script, but I'm going to export this grid VRN to file and then share that with you all.
I mean, what's the, you can run the code and write it, it's going to work.
All right, so let me just do a quick solution here, at least a quick solution so you all can Keep following. I just want to export this and share with you, so then you can import and we'll keep going. Okay. Let me- So I'm gonna put that again on GitHub. So you're gonna have to bring that in. But let me first push it. All right, so I just pushed this layer. It's gonna be on the 03 data, and it's called grid vrn.geojson. So once you bring that from GitHub, move that into your data folder, and then what you want to do, I'm gonna do it here on my side, and then you can do on yours once you get to the stage, is you want to create this grid_vrn object. And then you just do read SF and then /data grid VRN. So once you again bring that from GitHub, move into your data folder, and then create a new chunk right below where we were creating the actual grid VRN. Create a new chunk there, and then just bring this by reading from file instead of creating in the script. All right, I'll give you here a minute to do that. Once you complete it, please let me know, and then I'll keep moving. And then for, I guess, Polly, if you could post this issue on GitHub, or this solution, I guess, as a GitHub issue, and then I will make sure to incorporate this into the future versions of the script.
Yes, I put on the GitHub.
Okay, perfect. Thanks, Polly. Were you able to do it, Aman? Okay. In Tifton, was everyone able to bring this from GitHub and read in?
Yes.
Perfect. All right. So let's keep moving then. So if you remember from lecture, again, we have the reference here because the reference is what is so it's good to have a reference on the field because that helps to have parts of your field that are highly vigorous, and we know they're not stressed by nitrogen. And then we extract the way that we're going to, well, let me take a step back. There are different ways of using the reference strip to create a reference for nitrogen application. One of them would be to take the average of NDRE values all across from the reference strip. That would be one way. There is another way of doing this, which is to use the concept of a virtual reference. I don't think we talked about this in lecture, so let me tell you what that is. So the virtual reference is basically, so some farmers, some situations, you may not be able to apply a very high nitrogen rate at planting to actually have a physical reference in the field, like somewhere that you know you apply more nitrogen and that therefore is sufficient in nitrogen. Some fields you may not be able to do that. So some countries, or perhaps some states in the US, but especially some countries, if you think of Europe, have limitations of how much nitrogen you can apply at planting. So if you're applying this algorithm In Europe, you may not be able to have that, to actually apply that high nitrogen rate to create the reference at plenty. So one solution to that, when you either do not have a reference strip or you cannot have one because of legal issues, we can use the concept of a virtual reference in the context of the equipment that we saw in the lecture, which is a high clearance applicator, variable rate applicator with the sensors mounted on it. The way that you would create the virtual reference is you would turn on the sensors, start driving the field, maybe for, I don't know, 5-10 minutes, making sure you're covering enough area that is representative of the nitrogen status of your field. So you would like to make sure that you go over parts of the field that are average, that are low, but also especially that are high, that have a high nitrogen status or sufficiency status, which would be parts of the field that have a dark green plants. Then the sensor is just collecting the data, is not actually applying it, but is building this histogram, this density plot of the distribution of NDRE in the field. And then we use this density plots, this histogram, to determine the reference value as the 95th quantile of that distribution. This is what is called a virtual reference. That's the virtual reference concept. In this case here, we do have a high nitrogen reference that we could use, that we did not need to do the virtual reference. However, I do want to show you how the virtual reference would work, because even though in this case we don't need, it's still the option that would be more flexible if you are to apply this algorithm to research or maybe to a farm if you're working with that. So we're going to take the route of using the virtual reference. And again, even though in this case, we did not need to use the virtual reference because we have an actual high nitrogen reference. All right, so to create our virtual reference, again, it's going to be the 95th quantile of the NDRE statistical data distribution. So if you come here in the next chunk, we're going to use a function called quantile, which you have seen before already in this class. The data that we want to extract some quantile is the pred_NDRE $NDRE. So we're basically going inside of the stars object and really making sure that it only looks into that NDRE data. Then we're going to use here, the next argument is what is the quantile we want to extract, which is the 0.95. And if you remember, all these statistical summary functions like minimum, maximum, mean, median, quantile, and others, if you have NAs in the data, it will return NA unless you change the NA.rm to be equals to true. So that's what we have to do here. All right, so if you run this, and you check it out, the 95th quantile of the NDRE distribution for the whole field, so 500,000 and some pixels, is 0.31. Now, this is going to be our reference value. This is what we're going to compare each one of those cells in our grid against and say, this is our reference, calculate the sufficiency index based on this reference. This is the value. Now, I left you the code here for us to just, I think you have all the code. I think I left you all the code. If you just go ahead and run it, we're basically taking that same NDRE data, creating a density plot, and then placing a vertical line here on the 95th quantile of that distribution, which is our virtual reference. So again, this is a statistical distribution for all the pixels of NDRE for this field, and we are extracting here the 95th quantile of this distribution, which is right on this red line, which matches with the value that we created here of 0.31. This is what the virtual reference is. In our case, so if you think about it, if you are creating the virtual reference with the proximal sensor on the application boom and the high clearance applicator, you are limited because you're not going to be able, I mean, you could if you wanted, but it would not be efficient for you to drive through the whole field just collecting NDRE data without applying nitrogen, just to create a representative histogram to then extract the 95th quantile. So if you have the proximal sensors, the recommendation is that you drive around the field, I mean, not around, but drive in the field for about 5 to 10 minutes to collect enough data that represents the field. In our case, we don't have the limitation. We have an imagery for the whole field already. So we're basically extracting our 95th quantile based on the whole field data, which is very useful and is one of the benefits of using the imagery instead of the proximal sensor. All right. Well, I guess any questions about this before we keep moving? Mm-hmm.
So if we imagine doing the virtual thing, then there won't be a single strip, right?
Right. So Aman here is asking if we do the virtual, there's not going to be a single strip of reference. So in this case, we did have a strip of reference, but all the data from that strip is contributing to this histogram. Actually, all the data for the whole field, including from the reference, is contributing to this histogram.
But don't have, as you mentioned, some of the cases they don't, due to some restrictions, they don't have like a reference nitrogen. And
That's a great question. So Aman is asking, well, okay, so we're doing the virtual reference, which one of the benefits is you don't have to have a physical reference on the field. You don't have to over apply nitrogen to some parts at planting. But in that case, wouldn't that still change the virtual reference? So let's say if this field here did not have a reference at all. It was just whatever the grower had applied, which was 145 pounds nitrogen per acre. The concept of the virtual reference would still rely on the fact that that nitrogen rate that you applied would still create variability in crop response. So you would still expect to have parts of the field that would have higher nitrogen sufficiency status and other parts that would have lower. It's almost like if you were to come to this plot, and really I think the reference, it may be one of these two here that are really looking good in this scale here, looking more orange. One of these two is the reference. If you do not have the reference, you would still have all the other data for the rest of the field. And as you can see, you do have parts of the field that are really high as well, even though they're not part of the reference. So that is the assumption, right? It may not be completely true, but the assumption is that even if you don't have a high nitrogen reference, as long as you're using data for the whole field, you should still have parts of the field that have sufficient nitrogen in the data. And that's what you need then to create a histogram that is representative. Yeah, great question. All right, so let me go back to our chunk here. Okay. So if you remember from our lecture, we had the algorithm, the Holland-Shepard's algorithm. We need to calculate the sufficiency index. The sufficiency index is going to be a ratio, in this case, of NDRE, for where we could apply nitrogen, divided by the NDRE of the reference. So we already have our reference NDRE, which we just calculated above. And now the next step is going to be for us to calculate the NDRE of what we call the field NDRE, or the NDRE of the part of the field that may receive a variable rate nitrogen, which is going to come back to each one of those cells that we created on the grid. So the first thing that we have to do here is let's go ahead and crop, in this case, actually truly crop our NDRE layer, which right now is for the whole field, to only contain the values for the strips that will receive VRN. So if you come on grid NDRE, let's start typing here. We're going to call that stars object pre-NDRE. And to crop this to only contain our grid cells, we're gonna call the function st_crop and then give it the grid_VRN SF object. If you run that, it may take just a quick moment here to go through. And then if you print grid NDRE, you're gonna see it is still a stars object. And now I want to plot it so we can actually see what happened. So on the first three dots here, we're gonna call geom stars to plot that layer. We're gonna say data equals grid_NDRE. So if I just run up until this point before adding a plus, this is how that looks like. So as you can tell, well, first it is a geom star, so that's why it's not looking like our field. But you see that we only kept the pixels for the sensor-based strips. Now I want to bring here the actual sensor-based strips so we can visualize them. So let's add a plus after the geom stars, delete the three dots that you see there. And we're gonna call geom SF, where the data is gonna be equal to grid_VRN. And we want to have a fill equals NA so we can see through them, and add a plus at the end, and then we can run. This is what we look like. So right now, we clipped our NDRE, or we cropped our NDRE raster layer to only contain the pixels that intersect with our grid cells. All right. So now, if you think about it, each one of these grid cells have many pixels, right? We still have a lot of pixels in each one of these grid cells. And if we want to create a variable rate that is going to be specific to each one of these cells of this grid, we have to come up with the average NDRE for each one of these cells, which right now we don't have. That is going to be our next step. So now if you come to the next chunk, so I have some text here basically saying what I just told you. But if you come to the next chunk, we're gonna give the assignment symbol here. We're gonna start with our grid_NDRE, which is the object that we just created above. So this one here that has all the pixels that from the original image, but for each one of our cells of the grid. We're gonna pipe this into a function called st_extract, where here we're gonna give our grid cells. So the grid cells are under this object called grid_VRN. This st_extract function has an argument for fun, which is the function you want to apply to each one of the cells. I want this to be mean. You don't have to give the parentheses here, it's just the word. And I want to say na.rm equals true as always, to make sure that if there are NAs there, they are ignored and we still get a value back. If you run just this part here, it may take just a quick moment to go through because it is averaging a lot of pixels within each one of those grid cells. So we're just going to wait until it goes through here. You know what? I just noticed I forgot something on this code that I wish I had saw earlier before we ran and it was going. Let me see here. Okay, it just finished running, so it didn't take that long, at least not on my side. I think maybe on yours was even faster. But after we do the st_extract, if we just print grid NDRE average, it is a stars object. I do want to transform this to be a vector object. So we would come back to the code here. Right after st extract, you would add a pipe and use st as sf. We're gonna have to run it again. So just go ahead and run that one more time. And as it's processing, we can just wait a moment for that to happen, and then we'll keep going. But again, the goal here on this step is just to calculate the mean NDRE within each one of the cells in our grid. And again, we're just using the cells for the variable rate strips on this study. If this was an actual grower production system, it was not a study, you would create a variable rate for all strips, right? Not just some of them, but for all strips, because they would represent the whole field for this grower. All right, so it just finished running for me. I left you all the code to make this map. So is the NDRE map that we have now an average for each one of the cells rather than a whole bunch of pixels within the cells. So if you look right now, you will realize that each one of these cells on the variable rate nitrogen strips only, each cell now has one value. We average all the pixels within the cell to get one value for each cell only. And therefore, we basically coarsened the sensor information to be at the cell level. If you were to compare this with this, right? So this, we still have all the pixels. You can see variability inside of the grid. On this one, you cannot. It is one value per cell. Now, all the values you're seeing here are the VI field in that sufficiency index. They are the numerator in that sufficiency index. And so now we're going to, I don't think you have to worry. Yeah, because I don't think they should be here anyways. Somebody's trying to open the computer lab door. So these are the VIs for the field that we're going to use to calculate the sufficiency index. Are they knocking on the door?
Yeah.
Sorry everyone, give me just a second here. Somebody's knocking on the door. Okay, we're back. All right, so let's just revisit here where we are again. So we basically now we have our reference value, we have our field value, which is the value for each one of these cells. And now we're going to calculate our variable rate, or first our sufficiency index, and then our variable rate using the sufficiency index after that. I think that this is probably a good point for us to catch a quick break. And so let me stop here. I want to give you off a 5-minute break. And then once we're back, we're going to calculate SI and then the variable rate as well. So let me just put 5 minutes here and then we'll catch a break. Oops. All right, so let's come back to the code. So our next step is going to be to calculate the sufficiency index. So if you come here to the next chunk, that's what we're going to do. We're going to start off with this object that we created above, which is the grid underscore NDRE underscore AV for average. If we just print at this point, we have 759 features, where each one of those features is one cell in our grid that will create a variable rate prescription. And the NDRE column represents the field VI, right? Which is the numerator of our sufficiency index. If we want to then create the SI, the sufficiency index, we're gonna have to divide this by the reference, and the reference is a fixed value. So that means we're gonna have to have a column that has the reference value. Because we're creating a new column, we're gonna use mutate. I wanna call this column here as NDRE underscore ref, to mean that's the reference. And if you go back to our code, you're gonna see that we created an object that has this value, which is the VRN underscore ref. If I just print VRN ref, that is our value of 0.31. So now if you run this code here with the mutate, and then you print the object SI, you're gonna see that we have the NDRE column still there. We have the geometry column, but we have the NDRE ref column as well, which has the same number going all the way down. Because again, we just have one reference value. That's why we have just one, the same value for all the rows here. All right, so now we have our field VI, we have our reference VI. Now we can calculate our sufficiency index. So if you just give it a pipe, come after the comments, we're gonna call a mutate again. And I wanna call this column SI to represent the sufficiency index, which really is just the ratio, right? It's just the ratio of the column NDRE divided by NDRE ref. That's all it is. So if you run this and you print the object SI, you're gonna see that now, so we have our NDRE values, we have our NDRE ref value, and now we have our sufficiency index. So the sufficiency index is basically how, you can kind of think of it as the percentage or the proportion to which your field value is similar to your reference. So at a sufficiency index value equals to 1 means that your field vegetation index value is the same as that of the reference, and therefore it's sufficient in nitrogen. Now, as the SI decreases, it could go, I mean, it could be a very small value, but most of the time you're going to see perhaps the lower values being around 0.6, 0.7. It means that it has, let's say, an SI value of 0.7. It means that it's 30% less healthy than your reference. You can kind of think of it from that perspective as well. So now we have this relativized term. And again, we talked about the importance of why we're using, so why does this algorithm that we're using is using the sufficiency index and not just the NDRE value? Well, if you don't know the answer to that, I would say go back and watch the lecture again, but there are some good reasons for that. So we're not using the vegetation index value anymore after this point. We're using the SI because the SI is relative to a reference from that field from that year. All right, so let's go ahead and now plot so we can see a map of the sufficiency index. And now I'm gonna ask for somebody to help me here. So what function do we need to show the SI? Amandip said geomsf, that's right. So geomsf is what we need because SI is an SF object. we're gonna say data equals SI. On the AES, we will specify that the fill will be equal to the SI column. And then outside of AES, I want to say color equals NA. So we do not have the outline of those cells. Then add the plus after the GeoMSF and go ahead and run it. So this is what we see. It may still look similar to the NDRE map, but now it's in a different unit. It's in a unit that, well, it's a unitless measure because we divided two things that were the same. But it's basically a sufficiency index that the higher it is, the more nitrogen that part of the field has. Or if you think in the opposite terms, the higher is the SI, the lower will be the variable rate that will be required for that part of the field. We can still see some patterns here that are related to the field itself. So all these strips receive no nitrogen at planting, but you still see variability across the strip, and that is coming from the native variability of the field. And that's, again, the reason why we're going to use variable rates, because we want to apply more where more is needed and less where less is needed. Okay, so we had a map of NDRE. We used that to extract the reference, one value. We then had a grid for which we used the grid cells to extract the mean NDRE for each one of the cells. And that became our field vegetation index value. Now we have the field VI, we have the reference VI, we divided them to get the sufficiency index. So we just got one part of the algorithm done. If you remember, other parts of that algorithm were to give a value of the economic optimum nitrogen rate. Again, for this algorithm, that could be the rate that the grower has been using, or maybe if a nitrogen study has been conducted in that field, it could be that rate as well, coming from a nitrogen study before this growing season that we're working with. So we need to know that rate. We need to know if there are any nitrogen credits, and then the SI. We already have the SI, the sufficiency index. So now we're going to incorporate the EONR and then some credits here that we could use. So what we're going to do is on this next chunk here, the VRN chunk, to give an assignment symbol, we're going to start off with our SI object, give it a pipe. We're going to first set up our variables, or our constants, I guess I should say, for the total nitrogen rate that's required, what was applied pre-plant already, and if you have any credits for any type of credits for this field, and we're going to have some. So if you come after this all in pounds per acre comment, give it break line. Let's do a new mutate here. Our NOPT, so on the algorithm it's called NOPT, but this is the EONR. We're assuming it to be 229 pounds of nitrogen per acre total. This is what we're assuming that the crop for this field needs to optimize yield. Give it a comma still inside the mutate. Some credits that we need to add here is the application of nitrogen prior to the side dress. So if you apply any nitrogen at planting, you need to say that here. In this case, for the sense strips, the N pre, or the nitrogen pre-plant, was 0. So that's what goes there. However, the previous crop on this field was soybeans. And at least in Nebraska, soybeans give a credit of 20 pounds of nitrogen per acre. So we have here an N cred, a credit of nitrogen coming from the previous crop, which is equals to 20. So if you run the chunk until here, so before, don't add a pipe yet, but just run until here and print VRN at the end. You're going to see that now we have the columns SI, which is changing space based on the sensor. We have the nitrogen optimum, or our EONR, which is not changing space, it's a fixed value. we have our pre-planned applied nitrogen, which is all equal to 0 because the census strips did not receive any nitrogen. And you have the nitrogen credit from the previous crop that was soybeans, which is 20 pounds of nitrogen per acre, which is also a fixed value. So if you notice here, of all the inputs of the variable rate algorithm, the only one in this case that is changing spatially is SI. Everything else is a fixed value. It doesn't have to be this way. If you had your anything else, so maybe you have different optimal nitrogen rates for different parts of the field, you could change that here. Maybe you applied half of the field with a pre-planned rate and the other half no pre-planned rate. You could change that here as well. Same thing for credits. So in our case, the only spatially varying input of the model is the SI. The others are fixed, but they could be varying as well if you have that information in a variable format. Okay, so we have all of our algorithm requirements. We can go ahead and calculate variable rate nitrogen. Give it a pipe here, come on the next mutate. I left you most of the things for you, especially because I did not want there's a lot of parentheses and things that you have to be careful that you put them in the right place. So I just wanted us to have a consistent format in this case. So I gave you the sensor part of the algorithm already, which if you go back to the lecture, is the square root of 1 minus SI divided by delta SI, and delta SI is assumed to be 0.3. Now there is the other part of this algorithm, which is the non-sensor part of it, which is where we put here the N optimum. So the first three dotted points there, replace them by N opt. So N opt is the total rate that we think this crop needs. From the N opt, which in our case is 229, we're going to remove the credits. In this field, we have, well, we can type here on the next three dots N pre, even though it is 0, but I still want to have in the formula just so we are aware that this is one of the credits, even though in this case it would not make a difference because it's 0. So N opt minus N pre minus N cred, which is from previous crop. So replace the last three dots with N cred. So again, notice that the first part of the algorithm is just saying how much the crop needs, N opt minus credits. Whatever is left, so 229 minus 20 minus 0, it will be 209. 209, that rate is going to be modulated by the SI. Now the SI is going to tell how much that 209 should be. Should be lower than that, should be higher than that. Now, if you run this and you print VRN, you're going to have now your VRN pounds per acre column that has your actual rate, right? So we see values here like 207, 88, 166. These are the rates that would be applied to this field. Now, I want to, well, before I keep moving, maybe let me just check. Anyone has any questions about this? All right. So let's keep moving. If you go to the next chunk, I think I left you all the code there. This is just to do a density plot of the variable rate nitrogen prescription. So we understand what types of rates are we applying on those plots. So if you check here, our rates are ranging from just above 50 pounds of nitrogen per acre all the way to maybe 270 pounds of nitrogen per acre. So as you can see, there is a lot of variability in how much nitrogen each one of those cells is receiving. And that variability is coming from the fact that plots that have a high SI or cells that have a high SI are receiving a lower nitrogen rate, and cells that have a low SI, meaning a lot of stress, are receiving more nitrogen. And if you recall, the rate around which the sensor is modulating the rate is 209. That is the rate that the crop needs, which would be around here. So we see that the majority of the field is receiving less nitrogen than you would have applied if you were applying a fixed rate. And then just a smaller portion of the field is receiving more nitrogen than what would have been applied if you were using a fixed rate. All right, so now I want to do a map of the VRN application on this chunk here. What we're going to do is replace those three dots with a geom SF where data equals VRN. On our aesthetics, I want to say fill equals to the VRN underscore LBSAC. I want to show the rate, so that's the column that has the rate. And then outside of the AS, color equals NA. So this should be what you need. Oh, I forgot my plus. Don't forget to add a plus after the GeoMSF. If you run that and you print it, now this is your map. Now you see again that we have, this is the map for the variable rate nitrogen that's going to be applied. What I do want to do on the next chunk is to combine our NDRE map that we use to create the prescription and have that side by side, or maybe one on top of the other, with the VRN map, so we can interpret both of them together. I left you the code here. I don't think you have to do anything. So just run the next chunk. You're going to be able to see them side by side, or one on top of the other. So the first one here is NDRE. The second one is the variable rate nitrogen. What are you seeing? What are the relationships you can observe when comparing the NDRE, which is related to crop health as relates to nitrogen, and the variable rate prescription? Let me ask Luke, what do you think? So if you are saying something, I think you guys are.
Sorry, we were muted.
Okay.
I just said that the colors were inverted and that they're negatively related.
Yes, that's exactly right. So we see that where we have, so if you look on NDRE first, where we have lower NDRE, we have a higher rate being applied. And where we have a high NDRE, we have a lower rate being applied. That's exactly it. So it's applying inversely, right? Where there is more stress, we're applying more nitrogen to recover. Where there is not, and where there is no stress, where the crop is really similar to the reference, we're applying less nitrogen. Still applying some nitrogen, but a lower rate, right? All right, good deal. So now let's go ahead and export this. If you were working with a grower that was applying this, you would basically use a pipe. What I want to do here is only keep the variable rate prescription and the geometry. So let's do a dplyr select, where I want to keep the VRN pounds per acre column and the geometry. So the grower does not care about SI, NDRE reference, and everything else, right? They just want to know the prescription. So now we pipe this into a write SF function. I want to export this to output. So /output. Now, this is, ideally, you would be doing this to actually be applied on the field. Therefore, it's going to be required to bring this into a equipment. And as we know, the variable rate or variable rate equipments that can take this are probably going to require a shapefile. So we're going to create a shapefile. With that, as you know, the shapefiles take at least 4 subfiles to be exported. If we come on our output folder here navigating, I want to come here and create a new subfolder inside output. And I want to click on this link on this button here to create a new folder. And I want to name that VRN. I want to do that because imagine if you have many files you're outputting, it's easier to have all the files of a shapefile together in a subfolder than having them with other plots and maps and things. So going back to your code, after the output, I want to type VRN, which is the folder name that we just created inside of output. And now I want to export this as vrn.shp. Give it a comma. We always need to say delete underscore gsn equals true. If you run this, let's see, it gave me a warning. But let's see if it worked. So if I navigate to output and VRN, I still see my 4 files there, including the shapefile. So although at least on my side, it gave me a warning, it seems like it still worked. So these are the files you would bring into a variable rate prescription monitor. All right. So one cool thing about this is that we can actually check the results of the VRN application. So as I was telling you, this was a study where VRN was applied in those strips. The difference is that they did not apply the rates the way that we calculated. They applied the rates using the proximal sensor mounted on that sprayer boom. So they did apply variable rates at that V12 stage, which is when we have imagery for. And because they did have those rates applied, they went back to this field when corn was tasseling and took another imagery of this field, not to create a variable rate prescription, but just to check the effects of the first VRN application they did. And we do have that imagery here. So let's actually take a look at this imagery and see what we can learn from it. So I left you here the code. So this is the post NDRE. We were working with the pre NDRE. Now we're working with post. So the one after the variable rate application. I left you the code to read it, downsample, and rename, just like before. So make sure you run that. And now on the next part of the code, we're basically going to plot it so we can compare things. I left you 3 dotted points there, which are the ones we're going to be editing to make this plot. We're going to be using geom_stars because this is a raster file that in R was imported as stars. We're just going to say data equals to post_NDRE and then add a plus here, and then you can go ahead and run it. You should have everything else. If you run it and then you print, I guess, this is what we're going to see. This is what we see. So I guess we can take a quick moment here just to try to interpret what we're seeing. So maybe let me go to Tifton and ask somebody that I haven't heard much from today yet. Benedetta, can you help me to interpret this plot? What do you see there? And you're muted, just in case.
Well, here I can see that I kind see the pattern of the people,
Mhm.
and I can see that the higher value of there are some two strips with lower values of NDRE
Mhm.
in the middle of the field, and everything else is pretty much high.
Perfect. So something that we can notice here is that although if you really get closer, you can see a little bit of the east-west strip, but not as evident as before, right? Before it was really clear, the east-western pattern, which that was the pattern associated with the pre-planned nitrogen rates that was applied. So basically one thing to notice here is that is not as clear that eastern-western gradient that we saw before we applied the side dress application. meaning that our variable rate was able to recover that stress to some extent. Something else to notice here is that even though the effect that we saw earlier on the image before the application, that was the effect associated, or the eastern-western effect was the treatment effect. But even at that point, we could still see some of this north-south effect as well. Here at Tesseling, at VT in corn, we cannot see as much the eastern-western effect, but we can definitely see the north-south effect. And that effect is because of soil properties. That those parts of the field that you're seeing as darker in DRE, they're very sandy parts of soil in this field, and therefore we fixed the nitrogen rate effect that we had, but still the underlying effect of soil type is still making a huge impact on crop health on this field. So that is something interesting to notice, right? To kind of realize that while we can use variable rate of anything, with the goal of perhaps overcoming some of that soil variability, but in some cases it may be so strong that it's still coming through the crop as we measure in DRE. So it's just an interesting pattern to notice. And if you go to the next chunk, I don't know, so if this is gonna work on my side, let's see. If you just run that chunk and you have a map view and you bring Esri. Yeah, so Esri, for some reason, I mean, when I do the change in the plot, it is hiding away my layer. But basically, what I wanted to show you here is if you are able to toggle on and off your NDRE, you would be able to see that these parts of the field are parts of the field that are a little bit eroded and have more sand on them. And that's what's causing those parts of the field to be lower NDRE. Perhaps we could have even applied even a higher nitrogen rate than we did. Even those areas would still come out as lower health just because it's that underlying limiting factor of the soil itself. So this is something interesting to notice between the pre and the post VRN, or yeah, the pre and post NDRE data that we have here. Lastly, I just want to combine the pre-NDRE map, so the NDRE map that we used to create the prescription, with the NDRE map that we collected at Tesseling, that we used to check for the effects. So if you just run this next chunk, you're gonna see them one on top of the other. And this may help you to really understand what we just talked about. That on the first one, before we apply the in-season nitrogen application, we can see that there is a east-west pattern. That is because of the treatments. And even at that point, you could already see this north-south pattern. That was not because of the treatments, that it was because of the soil underneath it. And then on the NDRE post, which was at Tesseling, you do not see as much of the east-western effect, but you see very clearly the south-north effect, which is still remaining there because of the soil differences across this field. So I think it's a really cool example to explore. All right, so that basically wraps up our exercise. I just want to go through a quick summary. I want to open for questions, and I have one thing to ask you after this. So in a quick summary here, we imported UAV imagery in the form of normalized difference red edge index, or NDRE. And that was data obtained at the V12 growth stage in corn in a study in Nebraska. That imagery was used to extract the reference value, create a VRN grid, and then extract the NDRE average values within each one of those grid cells, combine those in the sufficiency index, and then bring the sufficiency index into the Holland-Shepherd's algorithm to calculate a variable rate nitrogen prescription for the field. After that, we exported this prescription as a shapefile, and then validated our variable rate nitrogen treatment application with post VRN imagery, in this case, at the crop growth stage of tasseling. All right, so any questions about this exercise? All right, I don't hear anything. So I'm going to ask you to do something. So I believe next Tuesday, we're going to be working with satellite imagery. Part of that is going to be to download satellite imagery through R from a given field. With that, for you to have access so you can do it yourself as well, and not just me giving you the images already, but I want you to learn how to download the images on your side, you're going to have to, let me just pull here. You're going to have to register for an account with the European Space Agency. Let's see where I have here. All right. So this is the address that I wanted to go to. So it's https://dataspace.copernicus.eu. Want you to go to that address. I'm going to copy on my side. I know that you don't have this on a script, so you're going to have to type on your browser. But I want to open that here on my side as well to show you. Once you go on that website, I want you to go here on login. I already have a login, but you probably, I mean, if you have not used it before, you're not going to have a login yet. So go ahead and click on the register button. So we're going to go there and need to register for an account. If I remember well, I don't know if they give you immediate access or if they're going to send you an email later saying that you are registered and then that you have access. But you will have to have registered and already be given access to work on our exercise of next Tuesday. So make sure you do register, especially if you can do that now. I think it's going to be useful, because if they do require some time to make a decision on your registration and give you access, you do want to do that today to make sure you have access by next Tuesday. Once you register there, that's all I had for you for today. And so you can go ahead and save your script from today and close that project. I also want to come here and open an issue on GitHub so you can claim your attendance. Let me do that right now. Right, I just opened the issue. Make sure you claim your attendance on GitHub. And if you do not have any questions, you are dismissed. If you do have questions or want to talk about something related to class, I'm going to stick around until 4:20. So we have about 7 minutes here.